Mr. True. In this video, we are going to do two examples of related rate problems in calculus. And just a little hint of what's coming up, they're going to be stories that involve right triangles and some geometry of those. This is our second video in the series, so we are not going to have written out all of the steps that we want to follow as we solve these type of problems. If you need to see those steps, I'll put a link in the description below to part 1 of this series, so you can go back and reference that if you need to. But hopefully we do a good enough job that it just makes sense from watching a couple of examples. So what do we have going on here? We have a rotating light that casts a beam of light on a wall 40 feet away. The light is rotating at 15 revolutions per minute. How fast is the beam moving down the wall? So think about you holding a flashlight and you're putting it out there, and there's that like hot white circle of light. How fast is that light beam moving down the wall when the beam makes an angle of 60 degrees with the perpendicular line from the light to the wall? And I think what we'll do is we'll put a nice good sized picture here, get it all set up, and then come over here and erase the words so we have some room to do the math and see the picture at the same time. And that is important. Yes, there's steps to follow when doing related rate problems, but it's really the geometry of what's going on, the type of measurements and values that are given in your story, and finally the question that is asked for that problem that's going to guide you through how to solve it. So there is a wall. Well, let's just say it's down here. There is a light source, and I'm going to put that above here, and that light source is rotating. Think of maybe a lighthouse, or maybe the light on the top of a police car, or just some kind of rotating light. And that light, let's see here, that light is 40 feet away from the wall. Okay, so that means that we have a measurement here going perpendicular, reinforced later on in the problem, but if you want to measure the distance between a point and a line, you want to move in a perpendicular type situation. So we have 40 feet, and that light is rotating, and I guess I'm doing counterclockwise just because we're always used to that in trig as that positive rotation angle measure. And we're going to be interested in a moment of time as this light is rotating and casting a beam of light on the wall that just kind of comes over here, hits the wall, and goes down the side of this building, if you will, or wall, at a particular moment in time. That moment in time is when the angle between the beam of light, if it was such as making a solid side of a right triangle, is 60 degrees with perpendicular. I'm not sure if that quite looks like 60 degrees, but I don't want to run off the board here. So that's 60 degrees. We are measuring from the light to the wall in a perpendicular fashion. So if this is a 60-degree angle, it may or may not become important in the problem. That means that the angle that the light beam is making against the wall is 30 degrees. We have this light rotating. This light is rotating right here at 15 revolutions per minute. So that light is rotating at 15 revolutions per minute. But if you think back about how we're going to use that fact that the light is making those rotations, it's making 15 full rotations in a 1-minute period, think about angular velocity in pre-calculus. Maybe you think of it as like angular speed, but speed is the absolute value of velocity, and speed doesn't have any kind of direction as part of its measurement. But we don't deal with angular velocity in terms of revolutions per period of time. We think of angular velocity in radians per minute. So if we do this rotation, it's d theta over dt, because the size of this angle between the light beam and the perpendicular segment to the wall, that's going to be constantly changing because the light is rotating, and that rate of change in theta over a period of time, that angular velocity from pre-calculus, we work with radians again per minute. So we're looking at how many radians are in a full rotation? Well, a full rotation is 2 pi radians. So this 30 revolutions per minute, though this is maybe a measurement that we're comfortable with, say like if you're driving your car and has a tachometer, it's going to be giving you revolutions per minute for that motor. That's going to be 30 pi radians per minute. And if I'm going to think of this as angular velocity, the fact that that's a positive measurement means that we're rotating in a positive rotation or counterclockwise. If it was angular speed, whether it was rotating clockwise or counterclockwise, we would have no indication of that. But here we go. So d theta over dt is 30 pi radians per minute. How fast is the light beam moving down the wall? Well, from the light source perpendicular, we have this distance down the wall that the light is traveling. So, if we put some numbers up here, let's say we call this, well, with the orientation I made it, we could call this x and y, but then that would maybe think that this is the origin of, say, a coordinate plane. So I'm going to call this a, and b, and c. Maybe a squared plus b squared is equal to c squared, because we're dealing with the sides of a right triangle. Or are we? We're being asked to find how quickly the light beam is going down the wall, so it's going to be some change in A. We're being asked right here, based on the question, to find dA dt, okay? Which is, while it is changing, it is basically a measurement of length. So at some point, maybe we need to figure out how far that value of A is down the wall. Okay, so we have a story that is developing into a picture of a right triangle. And what kind of geometry, what kind of math did we do in pre-calculus and trig dealing with right triangles? Well, if it was not trig, if we were given a story about a right triangle and everything was about lengths of sides or the rate at which sides were changing, that's Pythagorean theorem. A squared plus b squared is equal to c squared, where a, b, and c are all measurements of sides of a right triangle, the length of them. Well, this problem is involving a rotation of a light, a change in theta over time, and it's about a specific angle. Well, didn't we do SOHCAHTOA, sine, cosine, and tangent, where we were finding missing sides and angles within a right triangle? But so yes, we have a question dealing with angles in a right triangle. We're not doing Pythagorean theorem here. We're going to be doing some form of trig. Now, from the 60-degree angle that we're making between the light beam and the perpendicular segment to the wall, we have the use in working with the opposite side to that angle with the known side of 40 feet, the side that is adjacent to our angle that we're interested in. So we're going to set up the tangent of theta is equal to A over B. Now, as we learned and we talked about in our first video about related rates, if you put too much information into the problem in the beginning, you go to take the derivative and maybe just get a derivative of 0, or something's not, there's not enough happening, right? Related rates, our calculus is about math of motion, not static measurements. Any number that's in the story that is described as something being changed or is changing will not be or should not be put into our formula that we're developing until after we've taken the derivative of both sides implicitly, the derivative with respect to time, because you need that motion to go to be involved. Well, the 40 feet, the light is not moving away from the wall. The light is moving down the wall with a fixed distance of 40 feet. So now we're talking about the tangent of theta is equal to 1/40th of A. We can go ahead and put that 40 feet away, or that 40 feet the light is away from the wall, into our problem because it is not changing. But now what is changing? The angle is changing. The 60-degree angle is just a split moment in time. And A, Well, let's see here. Do we need to put in a specific measurement of A? Do we need to put in a specific distance that the light beam is from perpendicular into our problem? Well, we're not going to do that until we bring in that derivative and allow motion to occur in this problem. So we're going to take the derivative with respect to time of the left and the right-hand side, the derivative of tangent of theta, and the derivative of 1/40th of A. Of course, we can let that 1/40th, that constant coefficient, move out in front of the derivative with respect to time and say that that is 1/40th, the derivative with respect to t over A. And I know sometimes I probably talk too much and repeat myself as I do these videos, but you don't have an opportunity to ask me live questions during a recorded YouTube video. So just trying to think of all the questions you might have as we're doing these problems. And of course, once I skip too much, like in class, my kids start asking me questions. So the derivative of tangent is secant squared, but where our independent variable is not a perfect match to the variable with which we're taking a derivative with respect to. So as we do implicit differentiation with related rate problems, everything is going to involve the chain rule. So the derivative of tangent of theta is secant squared theta. Finishing up the chain rule, taking the derivative of what was inside the tangent function, we get the derivative of theta with respect to time. And then that is equal to, well, the 1/40th is going to kind of chill out up front, and the derivative of A with respect to t is 1/40th dA dt. Often, we might see this with the next problem, we may need to find that length of some other part of a geometric drawing that we have for that specific moment in time. It's all going to be dependent on what our derivative is asking for. But our derivative here, now that we are allowing that light to rotate and the distance down the wall to move with that fixed 40 feet the light is away from the wall, it's never actually asking for A. So what is this formula asking for? Well, it's asking for the secant, which is the reciprocal of secant is cosine. So we're looking at 1 over the cosine of some angle measure. Well, be careful. Remember, in calculus, we don't work, that's another reason why I picked this question, we don't work with degrees in calculus, we work with radians. And so we're going to be looking for the cosine of pi over 3. We're going to square that. We have that d theta over dt, the number of radians the light is going through in a minute is 30 pi radians per minute. That's going to be equal to 1/40th dA over dt. And the cosine of pi over 3 is 1/2, and 1 over 1/2 is 2. And 2 squared is 4. So we're going to have 4 times 30 pi. We have a division of 40 with the dA over dt, what we're looking for. So we're going to multiply both sides by 40 and make a note that we are finding the derivative of A with respect to t when theta is equal to pi over 3 radians. Make sure that you're indicating this mark here because the distance or how quickly the light is traveling down the wall is going to be dependent on that angle measure. The bigger the angle is from the beam to perpendicular, the faster that beam is going to be moving down the wall. And we're almost done here. If I've just stopped talking so much, we have 4 times 4 is 16, so we're looking at 160 times 30. We have 3 times basically 100 is 300, so 30 times 100 is 3,000, and we have 30 times 60, which is going to be 1,800. So our final answer is 4,800. That is a huge number. Pi, okay, pi what? A is a measure of distance, and this is a dA dt, which is the number of feet this light is going to be moving down the wall per some moment in time. So 4,800 pi feet per minute. And that is equal to dA dt when theta is equal to pi over 3. Now with questions like this, this is inspired by one of my textbooks questions. They kind of just arbitrarily switch it from a length of feet per minute to a number of feet per second, even though everything else in the story is using that measurement of time in terms of minutes. And there was no indication in the problem that you had to swap down to a smaller unit of measure. I'm sure the reason why is because this is such a very large number. And again, if this was a smaller angle, maybe just 20 degrees off of perpendicular, the speed, if you will, that beam is moving down the wall would be a smaller number. And indeed, the speed is just going to approach infinity as this angle increases and approaches 90 degrees or pi over 2, where the light would be perpendicular to the parallel to the wall. Example number two coming up right now. Example number 2 and the last one of this video. A boat is pulled into a dock by means of a winch for some reason. Maybe the boat's broke down. And the winch is placed 10 feet above the deck of the boat where you'd be tying off the rope. If the winch is pulling in the rope at 5 feet per second, determine the speed of the boat when there is 12 feet of rope out. Okay, I can see what's going on. There is some water. There is a dock. There is a boat in the water. Look at this beautiful drawing you get with our lesson. And maybe the engine's broken down. I don't know. Maybe it's a sailboat. Whatever. But we have some rope tied to the boat. And that boat dock is, for some reason, 10 feet above the deck of the boat. So I guess there better be a ladder to help us get out of this boat. And what do we have? Oh my goodness, we have another right triangle. So while that's, quite simple but maybe effective, it's not very effective. It's a little bit too small. So we're going to draw this triangle out, certainly not drawn to scale. We have a right triangle and some things are, well, changing here. Let's see what we have. We're going to call this, again, A, B, and C. And we're going to read the story again. A boat is pulled into a dock by means of a winch. It's 10 feet above, so the top of the dock is 10 feet above the boat. And yes, the tides change and waters rise and fall, but I think in this context, the story, that 10 feet is not moving, not changing. If a winch is pulling in the rope at 5 feet per second, okay, the rope is not the height of the dock, it's not how far the boat is measured from the dock, it's that angle here, or this hypotenuse that we have. So DC, since we have it labeled as C, DC over dt is equal to 5 feet per second. Does that make sense? Is that correct? Is, with C being the length of the rope from the dock to the boat, is C changing at a particular rate, a length per second? Is dc over dt, the rate of change of the length of the rope, is it 5 feet per second? Does that make sense? Are we adding 5 feet to the length of the rope for every second that goes by? Or are we taking away 5 feet because the rope is getting shorter? We're pulling the boat in. A lot of students will miss that. That's one reason why I picked this example for our video. So dc dt is equal to negative 5 feet per second. Okay, what else do we have here? Determine the speed of the boat. So another reason why I picked this is, what's the difference between velocity and speed? When you say that a particle has velocity, if it's moving left or it's moving down, then that is going to be a negative velocity. If it's moving right or up, that's a positive velocity, and speed is the absolute value of velocity. So we have to keep that in mind as we come to the end of our problem and we're trying to state a final answer. Make sure that since we're asked for the speed, we give a positive number. When the boat is, when there is 12 feet of rope out, so at the end of our problem, we have a specific moment in time as we're bringing this rope in and we're making it shorter. There's a specific moment in time that we're concerned about, and that's when C is equal to 12 feet. Are we going to be doing trig with this problem like the last example, or are we going to be doing a formula that only deals with the lengths around a right triangle? Does this question say anything about any angle changing? We could certainly figure that out if we were asked, but we're not given a rate of change of an angle, nor are we being asked to analyze how quickly any of the angles, the acute angles in this right triangle, are changing. So the story is letting us know that this is a question that is going to involve Pythagorean theorem. So we have a squared plus b squared is equal to c squared. If the story was maybe two cars coming towards an intersection, and potentially maybe one of them is about to run a red light and those cars collide, then all three sides of our triangle would be changing as the story progresses. Thus, we would be taking a derivative of the Pythagorean theorem in this format, where there's not a specific a, b, or c value initially placed into our formula. But the height of the dock for purposes of this problem, don't think about the tides changing, please. That is going to stay a constant 10. So b is never going to change in this problem. So we don't need to have a derivative of b with respect to time. And if you left it in there, the derivative db dt would be 0 because it's a constant. But it's just, I think, better to go a squared plus 10 squared is equal to c squared. Go ahead and plug that 10 in because it's a constant. It's not changing. We don't need to analyze its rate of change. And then take the derivative of both sides of our formula implicitly. Take the derivative with respect to t. And think about the chain rule as you do that, where we have an a, one more time, inside the power of 2. We have a c inside the power of 2, so don't forget that chain rule. The derivative of a variable base fixed exponent, you're going to bring that fixed exponent down, you're going to reduce that exponent by 1, and then you're going to finish the chain rule and have a dA dt. The derivative of a constant, 10 squared, is 0. And then on the right-hand side, we have the 2 coming down. We have the power on that c being reduced by 1. And we're finishing the chain rule. And so we're writing that dc dt. And writing like a prime and c prime, I don't like prime notation, sort of shorthand derivative notation when dealing with related rate problems, because it really kind of takes out that idea that everything you're dealing with is change over time. Well, what is, see now, okay, well we can divide both sides by 2. Get rid of that. So we have an equation, a differential equation, it's got derivatives in it, that is asking for a specific measurement of A and a specific measurement of C, as well as asking for the rate of change of the rope, and we were given that, and it's going to give us the rate of change of A, the rate of change of this horizontal distance, the distance between the boat and the dock. Well, that means we're going to have to kind of stop here, do a little bit of scratch work. We have a squared plus 10 squared is equal to c squared. Well, our moment in time as things are changing, that instant in time is when there's 12 feet of rope. And so we have a squared plus 100 is equal to 144, the result of 12 squared. That means that a squared is going to be equal to 44. And when you square root both sides, we get an a value right off the top of my head. The square root of 44, yes, it's 2 squared of 11, but the approximate value is 6.633 feet. Okay, so we have an A value to put in here, 6.633. We're being asked to find dA dt effectively. C is specifically 12, and we're pulling in negative 5 feet per second, so 12 times negative 5, and that's going to tell us that dA dt when C is equal to 12 is equal to negative 60 over 6.633, and that means that dA over dt when C is equal to 12 is approximately equal to negative 9.046. But we were asked not for the velocity of the boat, but the speed of the boat. So the speed of the boat when there is 12 feet of rope out is approximately 9.046 feet per second. And there's a couple of examples of related rates that involve right triangles. I'm Mr. True. Bam! Go do your homework.